Lesson 6, entitled Exponential Growth, U.S. Population and World Population. We'll have two instructional outcomes that we'll look at. The first one says to compare linear and exponential models of population growth. And the second one says to actually solve some of these problems involving linear and exponential growth. So in this particular lesson, the teacher really has one goal, is to let students look at different types of graphs and situations and decide and compare whether exponential growth is more appropriate, whether linear growth is more appropriate, and what makes sense and what does not. So in example number 1, it kind of starts off with a scenario where we have two students named Callie and Joe examining population data for a history report. Each of the students make a couple of comments after looking at each of their respective graphs. Callie says it looks like the U.S. population grew the same amount as the world populations, but that can't be right, can it? And then Joe responds, well, I don't think they grew at the same amount, but they sure grew at about the same rate. And Joe's defense is, he says, look at the slopes. So the teacher gives the students a few minutes to observe and to examine the graphs and think about what Callie and Joe both said. And so the teacher wants to know, what do you observe about these given situations and these graphs? So the students will look at them and they come up with different ideas of what is similar and what is different. What do they observe? For example, one student might note that this graph goes all the way to 7,000 and this graph only goes up to 300. But then same students might note that, well, this is from 1950 all the way to 2000. Same thing as this one, from 1950 to 2000. Another note students might observe and make, and there's no right or wrong answer here per se. It does say, well, this line, for the most part, looks like it's in the roughly the same spot or same design as this line here. And that's really what our whole discussion is about, and why Callie and Joe are making the discussions and the statements that they are each individually making. So we come up with the question, is Callie's observation correct? Why or why not? And then the same thing we'll ask again, is Joe's observation correct? Why or why not? So when we look at it, in simple terms, is Callie's observation correct? Why or why not? We would want to say no, Callie's observation is not correct. And for the reason being, keeping simply, if we look at just going across here, this is 6,000, and if we look at the bottom of this line, that's roughly in between here, so that's roughly 2,500, and so forth. And so if we come over here and look at this one, and we come across, we'll estimate this area to be about 280, and this is 150. So again, looking at Callie's statement, it says it looks like the U.S. population grew by the same amount as the world populations. Well, if we simply took the 6,000 minus the 2,500 and compared that to the 280 minus the 150, those numbers aren't going to be the same. So that kind of discounts what Callie said as an observation. We look at Joe. Is Joe's observation correct? Why or why not? And again, the answer would be no. They would not be. And for the most part along the same lines, he said look at the slopes. And so if we considered slope, remember slope is a design of rise over run, or the change of x, or the change of y over the change of x. We'll make that a 2 right there. We'll correct that. So that'll be a y squared, not a yy. But same thing. I mean, if you look at the slopes, your time, your run, and your rise, and then you run, and then you rise. Yes, your run is the same. They're both going from 1950 to 2000. But then same thing is this distance is our 6,000, and this is our 2,500. This is our 280, and this is our 150. So it's going to fall back on roughly the same idea that Callie had mentioned. And so there's no way that they can grow by that same amount because their slopes are not the same either in that particular design. So going forward and continuing to look at it, in part C it says use the world population graph to estimate the percent increase in the world population from 1950 until 2000. So here we are at 1950, here we are at 2000, and we noted that population was the 6,000 and the 2,500. We want to know the percent increase. So we know at the starting of our time measurement here at 1950, we had a population of 2,500. So if we take that 6,000, minus it by 2,500, and divide that by the original population that we had from when we were recording, and that's in 1950, so that'll be 2,500. When we take that information and solve it, well, 6,000 minus the 2,500, that is going to give us 3,500. Divide that by 2,500, and so what happens is you get is equal to 1.4. If we wanted to represent that as a percent, we would multiply that by 100, and so we would end up with 140% increase from the time we started in 1950. Now if we look at the US population and calculated the same thing, and so if we looked at the time in 1950, we had a population of 150 versus 2000, roughly a population, we're just going to call it 280. If you use 275, it's not going to affect the choice of the problem at all. So if we use 280 minus the 150, and our original population was 150, well, 280 minus the 150 gives us 130. Divide that by the 150, and so you end up with roughly 0.86, and as a percent that would be about 86% in that particular piece. So if we compare the two and looked at them, 86% versus the 140%, you can see the differences in the population increases. So that's what question E is talking about. How does the percent of increase for world population compare to that for the U.S. population over the same period of time? And so looking at that, you can see that one only increased by 86%, the other one increased by 140%. So while the lines look like they're going up by the same rate, it's important to note that this change in value, this change in vertical value here versus the change in vertical value there, is different, and that can sometimes be misleading to the casual observer when they look at one of these particular graphs. And so does the graph above seem to indicate linear or exponential population? And then explain your answer. Looking at this particular piece, most students will want to look at it and say, well, you know, it looks like it is a linear growth in each particular decision, and most students are going to explain their response as because it looks generally like a straight line. But again, that's what our discussion is about in this particular piece. So if we continue on and we move to example 2, example 2 is going to borrow from what we talked about in example number 1. So here we have a new graph, or a more refined graph for world population, and that's the graph that's listed right here. Now this one is from example 1. This is the graph that we just looked at from 1950 to 2000. So we again ask the students that same question. How is this graph similar to the world population graph example from example number 1, and then also how is it different? So some of the things that makes it similar is we note here that this goes to 7,000 and this goes to 7,000. That's important to note how it's similar. But one of the things that strikingly that's different is look at the original date here. It's 1700 versus the original date here is 1950. Now they both end at the same date, 2000 and 2000. And so that's kind of important to note. Another difference that students will very quickly observe in the graph is while this one appeared to be linear, when we first looked at it. Once we expand it or go all the way out to 1700, because remember this one here was just 1950. 1950 is right here. If we went all the way back in time to 1700 and look at it, we start to see more of an exponential curve start to develop over a larger amount of time. And so those are some of the similarities and differences that the teacher would be looking for the students to develop. In part B, does the behavior from the graph of 1950 to 2000 match that of what's shown in graph 1? And so the students would want to come up with that idea and say, yes, because here's what we're talking about, or here's what they mean, is in that perspective from 1950 to 2000, that is from here to here. And so that instance in its own right seems to be linear if you were to just take that single piece. And that's what this piece from here to here represents, and that's why it appeared linear when we looked at that given perspective. In part C, why is the graph from example 1 somewhat misleading? And students will come up with various different reasons, but for the most part we want to look at the fact that this one appears to have grown in a linear fashion because we're only looking at a very small window of time, 1950 to 2000. When we really look at it from 1700 to 2000, you start to see how that classic curve is developed. So we talked about in previous lessons how exponential curves really grow very, very small at the beginning. And then after a long period of time, then they will start to skyrocket and start to go up. And so that's why it can be somewhat misleading if you don't include enough data in your particular graph or table to represent what may be going on. In part D, they say an exponential formula that can be used to model the world population growth from 1950 to 2000 is as follows. And so they give us this information here, this particular formula, the starting population, right here in 1950 to be exact. What is the rate of growth right here, raised to the t power? This t power actually is a typo, and this t power should be out here on the outside, not on the inside, to where 2,519 is the population 1950, and t is the number of years after 1950. So they would say use this equation to calculate the world population in 1950, 1980, 2000, and so forth. I won't go through those in this particular example, but for just to kind of look at it for a minute, if we're talking about 1950, that's the year that we started, so that would be t equals 0 because that's their starting years. And the reason why that's significant is because that's our starting population. So in 1950, we would have 2,519. If we wanted to represent 1980, that is 30 years after 1950. So it's important a student notes that where t is, you're not going to put 1980. You're going to use t equals 30. When you plug in t equals 30 and you calculate that for 1980, you're going to get a population of 4,264. And then likewise, if you're talking about the year 2000, 2000 is 50 years after 1950. So we would let t equal 50. And then if you plug that in, the 50 in for t, and calculate that f of t, you would end up with 6,056 people in terms of that population. At this point, the teacher kind of turns it over to the students to look at a couple of exercises. This is exercise 1, recommended to be done in small groups. And so it presents a table of the U.S. population in millions for specified years. In 1800, we have 5 million. In 1900, 76 million. In the year 2000, 282 million. And so it starts by posing off two questions here. Part A and then Part B. If we use the data set from 1800 to 2000 to create an exponential equation to represent the population, we generate the following formula. And just a recap, where does this 5 come from? That is the starting point in the year 1800. What is this piece here? This is the 1 plus the percent in which it is increasing each year. If you wanted to note that formula from the geometric time we did before, that would be the ace of 1, or the beginning, times the 1 plus the rate raised to the t power. That harkens back to our geometric formula we talked about at the beginning of Module 3. So use this formula to determine the population in the year 2010. So remember, they're stating in Part A that 1800 equals 0. Well, 1900 is 100 years later. The year 2000 is 200 years later. They want to know in the year 2010. So if I wanted to add on to this table, if I want to know about the year 2010 in reference to 1800, that would be equal to 210. So that is what you would put in for t. So you would type in your calculator 5 times the 1.0204 raised to the 210 power, not 2010. You don't put the physical year in there for that piece. And so when you solve that and calculate it, you're going to end up with 347 million. 347 million as your answer. Your calculator may just type 347 on it, because remember, we're kind of changing the numbers as 0, 100, 200, 210. Note that this is written in, or represents, millions. So if we look at Part B, in Part B, if we use the data set 1900 to 2000, so we have a new starting point, meaning, in other words, let's just say we take this off and we pretend that the year 1800 is not part of our data. So now 1900 is our new starting point. So now our ace of 1 is now 76, as illustrated right here. That'll change our rate of growth a little bit, because we're accounting for a little bit less data in this perceptive. And so they want to know what would be in the year 2010. So again, if we set this as equal to year equals 0, this would be equal to year 100. And so 2010 would now represent 110. So we would put that in our calculator, our 76 times the 1.013 raised to the 110 power. And once we calculate that for the year 2010, we would end up with 315 million in that given scenario. So the question continues to follow up with Part C. Looking at our table again, the actual population in 2010, based on the U.S. Census, was 309 million. And so they're asking students, which of the following formulas, this one here or this one here, made better models for the U.S. population for the entire span of 1800 to 2000. And so if we go back and look at that data just alone, here we've got 347 million versus 315. So looking at that reason alone, students would come up and reason that the logical model that seems to fit right now would be this particular piece right here. Why? Because it would tend to reason and argue that the population growth in the U.S. has decreased over the last few decades, and not increasing as quickly as some of the prior estimates had predicted prior to that time frame. And that's not uncommon to think about, really. Models need to be tweaked or updated or redefined based on what current activities or levels are producing in our populations anyway. So if we look at letter D, they say complete the table below to show projected population figures for the indicated years. Use the formula from Part B to determine the number of years. And so while I won't do these in specific each time, remember, if we chose this particular model, the 76, 1.01, that's this one here, that started off with 1900 as 0. So it's important to note that if 1900 equals our 0 year, then we know that the year 2000 is going to equal 100. So if we go to 220, that's going to equal to 120. If we go up to 150, we'll continue to increase by that amount and so forth. So just be careful in working that out and define that. Try it, see if you can come up with the answers. Pause the video and come back. And then when you unpause it, the answers will be right here. So the answer you should have gotten based on this new model is 358 in millions, 528 in millions, and then 777 in millions. So again, if you have a difficult time or you don't know how to figure this piece out, again, we're starting with 1900 equals 0. Check with your child's teacher and they'll be happy to clarify that a little bit further for you. So then in part E, are the population figures you computed reasonable? What other factors need to be considered when projecting population? So this is just kind of a discussion between the student and the teachers or groups of students that are working with. And so they might say something like this, that these numbers do not necessarily take into account changes in technology, efforts to reduce birth rates, food supply, or changes in life expectancy due to increases of diseases or scientific advances. So students may come up with a variety of responses here, but different things that occur in our lifespan could cause us to have to further refine this model or redefine our population growth in these given situations. So the last exercise is an opportunity for the students to compare an exponential model to a linear model. And so they give this situation where it says the population of a country named Oz was 600,000 in the year 2010. So 2010 is going to be our starting point. The population is expected to grow by a factor of 5% annually of what it was the previous year. Then it tells us the annual food supply of Oz is currently sufficient for a population of 700,000 people. That's 100,000 more than what the current population is in the year 2010, and is increasing at a rate in which the supply of food for an additional 10,000 people per year. So as every year goes by, if we start with 700,000, the next year we could support 710,000, then 720,000, and so forth. So in Part A and Part B, they want us to take this information, write a formula to model the population of Oz, and is it linear or is it exponential? So the model for Oz is going to be exponential. We start off with 600,000. And we're growing by a rate of 5% every year, so that's going to be our 1.05. And then we're going to be raising that to the t power, the number of years since the year that we started. So the year 2010 will represent our 0th year, the beginning. And then in Part B, write a formula to model the food supply. That's going to be linear. The annual food supply of Oz is currently sufficient for a population of 700,000 people. So 700,000 people. And it's increasing at a rate of an additional 10,000 people per year. So we can support plus 10,000 more people per year as we continue to increase. It's important to note, if you haven't observed, that this is a geometric formula and this is an arithmetic formula. And so they say in Part C, at which point does the population exceed the food supply? And so if we do know that this is a geometric sequence versus an arithmetic sequence, if you were to go to your calculator and type in a geometric sequence, the 600,000 times the 1.05 raised to the t power, then we start to get an idea of what's going to happen. So if we kind of just started to write some down, we know that in the year 2010, then we have a population of 600,000. In the year 2011, if we take that 600,000 and look at what it will be based on our table, we end up noting that it's going to be 630,000 in this perspective here. If we look at the year 2012, we end up with 661,500. In the year 2013, we end up with 694,575. Now I'm going to fast forward and I'm going to go to the year 2015, and I'll explain why in a minute, but I am running out of screen space, so I'm just going to skip to that year. It's a year that I want to point out. And so if we talk about 765,768 roughly in that particular year. So if we did the same thing with the arithmetic, in the year 2010, we know that we will have 700,000. Every single year we're going to add 10,000 to that. So we know the next year after that it's going to be 710,000. In the year after that, in the year 2012, it'll be 720,000. If we go to the year 2013, that is 730,000. If we fast forward to the year 2015, that means 2014 would have been 740. 2015 would have been 750,000. 750,000. And that's the question we're trying to answer. At what point does the population exceed the food supply? If we look at the year 2015, the population versus the food supply, 2015 is going to be the first year that we look at that the population is larger than the food supply. Because if we look at previous years, 600,000, 700, 630, 710, 661, 720, 69.4, 730, but this one, 76.5, 750. And so at that point we end up with a population problem because we no longer have a food supply that can support this particular piece in that design. And so that's all I'm going to talk about here, just to give you the idea of comparing and what that does. If you need any other follow-up, again, I always mention go back, talk to your child's teacher, or if you have any questions, just let us know.